In this video, we're going to be looking at zeros of polynomial functions, in particular real zeros. We'll get into non-trivial complex zeros in a later video. Now, the most important thing for this part is to know this little bullets here section. All of these mean the same thing. So if the number c is a zero of f, that means when you evaluate f of z, it equals the number 0. If you use synthetic division and you look at the remainder when finding f of x divided by x minus c, so if c is in the box and the remainder is 0, then we say that c is a 0. So we've also done that in a previous lab. If c is a 0, x minus c is a factor. And if c is a 0, then if c comma 0 is an x-intercept, well then c has to be a real number. So if you find an x-intercept on the graph, it's automatically a 0. Okay. All right, so let's look at this first problem where they ask you what the zeros are. So again, we've touched on this before in previous labs. If you're going to find the zeros, then you set the equation equal to 0 and solve for x. That's minus a half. And so you can see what would make this equation 0. Well, if x is 5, if x is negative 3, or if x is a half. And so what I have in red here are the zeros. Now these are real numbers, and so if you have real zeros, they give you x-intercepts. So the x-intercepts are going to be the points 5, 0, negative 3, 0, and a half, 0. Okay. Now let's go on to the next part, find a polynomial with those zeros. So it's kind of covered up in the graph above. Sorry, and what we had up here. Okay. So if c is a 0, then x minus c is a factor. So for example 2, find a polynomial with zeros negative 4, 0, 1, and 7. So let's go through these one by one. So negative 4 is a 0. That's the same as saying x minus negative 4 is a factor. But of course x minus negative 4 simplifies to x plus 4. So x plus 4 is one of the factors. Let's go on to the next 0. 0 is a 0. 0 is a 0. And so x minus 0 is a factor. Now x minus 0 is just x. Okay, so that's where we get this second result. Then we're told that 1 is a 0. So if 1 is a 0, then x minus 1 is a factor in its formula. That's where we get that result. And then if 7 is a 0, x minus 7 is a factor. Okay, so this is where we get our individual factors. And so you can write a polynomial as a product of its factors. So find a polynomial with these zeros. You can write a polynomial by taking all the factors and multiplying them together. and you don't have to multiply it through. Okay, and that's your answer there. So there is a web work question just like that. Now we come to this next part where the degree, a definition is of a polynomial, is the highest power of x. So if I have something like that, then this polynomial has degree 7. It's the highest power of x. Now we have a theorem. The number of zeros of a polynomial function is equal to its degree. Now there's a little caveat there. It says if you count repeated zeros, the number of times they occur. We're not going to get on to repeated zeros until after we look at these two examples. So you're told to find all the zeros of this. Now, if I look at this, it has degree 3. So there will be 3 zeros. Okay. Then let's look at the graph. Because if we're lucky and we can spot an x-intercepts and they're easy to read, we can immediately say that those are the zeros. So here's a picture of it, but I'll also do it here for you. So let's get into here, and I want x cubed minus 11x squared plus 23x plus 35. And I'm just going to quickly double check that I've entered this correctly. Then I'm going to do zoom and the number 6, and it's going to give me the picture in a standard viewing window. Now I can change this window. Standard viewing window, x goes from -10 to 10 and the y values go from -10 to 10. I think I can take this from, say, -3, the x values, to 10, and I might leave the y values as they are. So I'm just going to change the x value and then press graph. Okay, this one has x-intercepts that are easy to see. There's one at -1. There's one at 1, 2, 3, 4, 5, and then 6, 7. So look at the graph. You can see that we have x-intercepts at -1, 5, and 7, and so they are zeros. So x-intercepts always yield zeros. Since the degree of f is 3, we have found our 3 zeros. Okay. Now, if you were asked for the x-intercepts, you'd give them as points. We weren't asked for the x-intercepts. I mean, it is correct to say there's an x-intercept at -1, 5, and 7, but if you're actually asked for what they are, give them as points. This one asked us to find the zeros. It had degree 3. There's going to be 3 zeros, and x-intercepts always yield zeros, and these were easy to read off. So this one you could do completely with the graph. Not so on the next one. Find all the zeros. Okay. So again, it has degree 3. So there's going to be 3 zeros. And let's look at the graph. So again, I'm going to get my calculator up here, and I'm going to come back here. I'm going to clear that. And now I have x cubed minus 7x squared minus 11x plus 77. And let me make sure I have entered it correctly. I'm going to go back to Zoom 6. Okay, so this could be refined a bit more. I might take the x value, say from -5 to 10, and I'd like to see what's going on more at the y, taking it beyond -10 to 10. So I might take that from -5, and then I might just try -20 to 20 for the y value. So this is very individualized. Then I'm going to press graph and see. Okay, I've got a better idea. I could probably make it a little bit better if maybe I take this from -30 to +30. So I'm just refining it. Okay. Now, here's the thing. I can see that I have 3 x-intercepts, but they are no longer whole numbers, integers, easy to read off. This x-intercept comes somewhere between -3 and -4, and I do not know what it is exactly. This x-intercept comes somewhere between +3 and +4. I do not know what it is exactly. But this one here, luckily, appears to be a whole number. 1, 2, 3, 4, 5, 6, 7. So this one, if we look at the graph of f, we can see there's 3 intercepts, but only one of them is easy to identify, namely the one at 7, 0. So we have a 0 at 7. I don't know where these are at. So what I can do is I can use synthetic division to get it into factored form, and then either use a quadratic factor or other things that I know. So I know that 7 is a 0. So if 7 is a 0, then we go back to the beginning. 7 is a 0. The remainder, so let me come up here. I know that 7 is a 0. And so now if I come here, the remainder when dividing f of x by x minus 7 is 0. So if I set this up with synthetic division, I should get a 0 there, and here it's going to give me the quotient. And I should be able to factor f, which is what I'm going to do. Okay. So I know that 7 is a 0 on the graph. So I'm going to do synthetic division. Now I've already done it here, but I'll just do it. And so I'm going to put all the coefficients. One times 7 is 7, and when I add, I get 0. 0 times the number in the box is 0. When I add, I get -11. And -11 times 7 is -77, and when I add, I get 0. There's your remainder, which means the number in the box is a 0. X minus the number in the box is a factor. And we can factor this now. It's going to be the divisor, which is x minus the number in the box, times the quotient. And this tells me the quotient. Here's the line. There's my constant, my coefficient for x, my coefficient for x squared. And so my quotient is going to be 1 times x squared plus 0 times x, which I will not write, minus 11. Now, if we were lucky, that could be something we could easily factor by looking at it, and it would be nice and have whole numbers, but it isn't. If we remember from the previous lab, if you have x squared minus a number, that will always factor. And if you're lucky to get something nice, that will factor nicely. So x minus the square root of 9 is x minus 3, and x plus the square root of 9 is x plus 3, because 9 is a perfect square. However, we don't have a perfect square. We've got 11, but the formula is still correct. So this will factor as x minus 7 times x minus square root of 11 times x plus square root of 11. And you can see what the zeros are. The zeros are 7, square root of 11, and the negative square root of 11. So which is what we had here. And the zeros were 7, square root of 11, and negative square root of 11. Now, what happens if you didn't remember that? And you've gotten to here. You've gotten to here, and you've tried the trick to factor that, and it doesn't work. Well, if you don't remember that, then you could always use the quadratic formula. So if you did not remember that, you could always use the quadratic formula. So if you get a quadratic that you can't factor using a trick or a rule, you can always use the quadratic formula to find the zeros. So if you want to find the zeros of that, then of course A is 1, B is 0, there's no x term, and C is a negative 11. And if you plug in the quadratic formula, you get that the zeros are plus or minus square root of 11. Okay, so you could still get the answer. And what do you type for square root? So if they want you to type the zeros, separate them with a comma, you'd have 7 comma, and then just SQRT, and then whatever's inside the square root symbol. Okay, now we come to, we mentioned something before about repeated zeros. What do they mean by that? Well, this is where the word multiplicity comes in. So the multiplicity of the zero is the number of times it's repeated. And if you have a real zero with even multiplicity, the graph will touch and bounce back at the x-intercept. If C is a real zero and has odd multiplicity, then the graph will cross through at the x-intercept, C comma 0. So without using a graphing calculator, match the formulas to their respective graph. And you want to make sure and do this exercise without a graphing calculator, because it will not always be the case that you can just simply put something into your graphing calculator and look at the answer. So let's look at the first formula. Let me go back. Okay, so the first formula is x minus 2 all squared times x minus 3. What are the zeros? Well, set it equal to 0, and you can see that the zeros, x equals 2 and x equals 3, will make the whole thing 0. So those are my zeros. Now, what about the multiplicity? How many times is it repeated? Well, x minus 2 squared is the same as x minus 2 times itself twice. And so what are the zeros? Well, 2, 2, and 3. So 2 is a zero that's repeated twice. So it has even multiplicity. 3 is only repeated once. So it has odd multiplicity. But you don't want to have to do this out all the time. Let's look at this. So if I want the multiplicity, how many times is this repeated? Well, this is repeated twice, so the multiplicity is 2. How many times is this repeated? Well, if there's nothing there, it's understood that the power is 1. Okay, so with the first one, 2 is a zero of even multiplicity. So if it has even multiplicity, the graph will touch and bounce back at, it will touch and bounce back at the 0 at 2, 0. Now, 3 is a 0 of multiplicity 1. It has odd multiplicity, so it will cross through at 3, 0. So I want to find a graph, first of all, that has x-intercepts at 2 and 3. This one does not. That has an x-intercept at 2 and an x-intercept at 3. Kind of hard to see. But it crosses through at 2 and it touches and bounces back at 3. And that's not what we want. Okay. Now let's go on to, let me just scroll this page down to the next ones. Okay. So I want an x-intercept at 2 and 3. This does not have x-intercepts. It has an x-intercept at 2, not one at 3, and it's got one at -3. So that's not going to be it. So none of these are it. All right, so by process of elimination, it's going to be this one. But this has an x-intercept at 2, and it touches and bounces back. And then it has an x-intercept at 3, and it crosses through. Unfortunately, I mean, I wish I could have made this bigger. Because what's actually going on, this is what's going on. So that's at 2, and that's at 3. So it is touching and bouncing back at 2, and it's crossing through at 3. Okay. So the answer to number 1 is D. Now let's look at number 2. X minus 2, x minus 3 all squared. To find the zeros, set it equal to 0. So 2 is a 0 and 3 is a 0. So we will have x-intercepts at 2, 0 and 3, 0. Now what about multiplicity? This has multiplicity 1. So what's going to happen is it's going to cross through, since it has odd multiplicity at 2, 0. Here, our multiplicity is 2. It has even multiplicity, so it's going to touch and bounce back at 3, 0. So I want crossing through at 2 and touching and bouncing back at 3. And so this one seems to fit B. Okay, so now with the third one, we have x plus 2 squared times x minus 3. What are the zeros? Well, -2 will make the whole thing 0, and 3 will make the whole thing 0. So I'll have an x-intercept at -2, 0, and an x-intercept at 3, 0. Now what about the multiplicity? This has multiplicity 2. It's even multiplicity. So it's going to touch and bounce back at our x-intercept. What about the multiplicity for this one? This has multiplicity 1. So we have odd multiplicity. So it's going to cross through. Oops, that needs to be black. It's going to cross through at 3, 0. All right, so here I have -2, and it touches and bounces back at -2. And here I have 3, and it crosses through at 3. And so that one's going to be A. Now, process of elimination, the last one will be C, but let's check why that's true. So the last one is x minus 2 times x plus 3 all squared. What are the zeros? Set it equal to 0, solve for x. If x is 2, it'll make the whole thing 0. If x is negative 3, it'll make the whole thing 0. So I'll have x-intercepts 2, 0 and negative 3, 0. Now, what about the multiplicity? This has multiplicity 1. So we have odd multiplicity, so it's going to cross, oops, it needs to be black. It's going to cross through at my x-intercept. Now, what's the multiplicity for this? That has multiplicity 2, so it's even multiplicity, so it means it's going to touch and bounce back at this x-intercept. So so here's negative 3, and it said it would touch and bounce back at negative 3, so that works. And here we have 2, and it crosses through at 2. And so the answer for the last one is C. Okay, so all of that is explained down here in the solutions and which one they match. Okay, so now let's find all the zeros of this. Well, our degree is 3. There will be 3 zeros. Now, if I look at the graph and graph this, I have an x-intercept at 3 and an x-intercept at negative 1. And what's happening at negative 1? It's crossing through. So we have odd multiplicity at negative 1. So it only occurs once or 3 times or 5 times. It can't occur 3 times because if you count a 0 the number of times it's repeated, then that would give us 3 zeros, and then we still have these to go with. So I'm going to say it has multiplicity 1. So it's only repeated once. Now look at 3. It touches and bounces back at 3. And so that means it has even multiplicity. That means it's repeated an even number of times. So it's repeated twice, or 4 times, or 6 times, or 8 times, etc. But we're only going to have 3 zeros, and if you count the zeros, the number of times they're repeated. And so I'm going to guess that 3 has multiplicity 2. And that works. So the zeros are going to be negative 1 and 3, but 3 is repeated an even number of times. So if it's repeated twice and I count these up, that will give me 3 zeros. So this is what we mean when we go back to this theorem. The number of zeros of a polynomial function is equal to its degree. Then in parentheses, if we count repeated zeros, the number of times they occur. And so for this one, it has 3 zeros, and we saw that 3 has even multiplicity, and so for that to fit, 3 will be repeated twice. Okay, if it's repeated 4 times, then you have more zeros than what you're allowed. This has degree 3, so there will be 3 zeros, and if we count any repeating ones, the number of times they happen. What about this one? Well, it has degree 4, and so there will be 4 zeros. Now I can see that I have an x-intercept at -3, and I can see that I have an x-intercept in 1. So -3 and 1 are zeros. But now, if I count them up, the number of times they're repeated, I should have 4. Now what happens here? This touches and bounces back at -3, so it has even multiplicity. What happens at 1? It touches and bounces back, so it has even multiplicity. So for this to fit with 4 zeros, then my guess would be that both of these have multiplicity 2, or repeated twice. So if I write down my zeros, the number of times that they're repeated, then I will have 4 zeros. Okay, so below, they want us to actually write a formula, and they give you a template for a formula. So I might try and make this a little bit bigger. Okay, so first of all, what are the zeros? Well, I can see where I have x-intercepts. So I have an x-intercept at -1, at 1, and at 2. So my zeros are -1, 1, and 2. Okay, but what's going on? Okay, so those are my zeros. Now, if c is a 0, then x minus c is a factor. So if -1 is a 0, then x minus -1 is a factor. If 1 is a 0, x minus 1 is a factor. If 2 is a 0, x minus 2 is a factor. And now, what about multiplicity? At -1, it touches and bounces back, so it will have even multiplicity. So that has to be at least a 2. And it could be a 2, a 4, blah, 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 but I want to make it fit this template. 1 and 2, they cross through, and so they have odd multiplicity, and so they are repeated at least once. So only once or 3 times, blah, blah, blah. If I'm going to make it fit into this. Now finally, f of x is a product of its factors. So I could have x minus -1 all squared times x minus 1 times x minus 2. And so this will fit now that a is -1, b is 1, and c is 2. If I was going to write this as a product of its factors, I would clean it up. X minus -1 is x plus 1 all squared. Okay. But to make it fit the template, I wrote it like that. Okay, so that concludes all of the examples that you need to do your web work. So that concludes this video.